Welcome. In this video, we're going to talk through some practice problems involving integrated rate laws. And these integrated rate laws are things that you should apply whenever the problem gives you information about concentration versus time. You might be given that information in the form of a data table with concentration versus time. You might be given it in graphical form. It might be written out a sentence in the problem, but whenever you see concentration versus time information being given to you, then you want to think, integrated rate laws. And where you can find these integrated rate laws is on your equation sheet in the kinetics section. They look just like this. There are 4 equations that we can apply, and which equation you apply depends on what the reaction order is. So this first equation right here applies to 0th order reaction. So if the reactant A is 0th order, then this relationship applies. This second equation is for first order reactants. So if you look over here, this is our regular rate law. So if it is first order with respect to A, then this is the integrated rate law that will apply. If the reactant is second order, this is what the normal rate law would look like. The exponent would be 2. When we integrate it, and this is a calculus term, you don't need to worry about how it works exactly. You don't have to do calculus in here, but just so you know, we did some math magic, and we took this regular rate law and turned it into this integrated rate law. So this third equation right here applies to second order reactions. So these equations are all given to you on your equation sheet. You do not need to memorize them, but you do need to know which is which, and you need to know when and how to apply them. That's what we're going to practice today. This fourth equation is a variation on the first order integrated rate law, and this is a half-life equation, and we'll talk about half-life problems in a different video. But this is also an integrated rate law. So because of these relationships, one useful thing that we can do with these relationships, these equations right here, is if we're given concentration versus time data, we can use that information to determine what the reaction order is. So this is just a different way of determining the reaction order. In a different video, we talked about the method of initial rates, where you could vary the concentration of the reactant and see what impact that has on the rate. This is a totally different experimental technique. In this type of data, what we're doing is we're just looking at the concentration of one reactant over time, and we're graphing it, and we're looking if that relationship is linear. So if we collect some concentration versus time data, and we plot it on a graph, and we notice that concentration versus time is linear, that tells us that the reaction is 0th order for that reactant. If it's first or second order, we will notice that this graph is not linear. So then we can try plotting some other things. So if we were to plot the natural log of the concentration versus time, if that graph is linear, that will tell us that the reactant is first order. If the inverse of concentration versus time is linear, that tells us that the reactant is second order. So there's 3 relationships, 3 graphs you want to consider: concentration versus time, the natural log of concentration versus time, and the inverse of concentration versus time. And depending on what the reaction order is, whether it's 0th, first, or second order, one of these corresponding graphs will be linear. And that matches with these equations right here. So if concentration versus time is linear, it's 0 order. If the natural log versus time is linear, it's first order. If the inverse versus time is linear, then it's second order. Here's another summary slide showing these different relationships and the equations there. So the types of problems you want to be able to solve involving integrated rate laws are: 1, if you're given data in a table or graphical form, determine the reaction order. So here's where we're going to be looking for which graph versus time is linear. This is the most common version you will see. Another thing you might need to do is actually plug some values in and solve for an unknown. So using the relevant rate law equation, and if you're given values of concentration or time or rate constant, you can use that integrated rate law, so that mathematical equation that we were showing right over here, to determine to calculate something, like maybe calculate the value of K, or calculate the value of T, or calculate the concentration. So let's go over a couple sample problems here. So this first problem, we've got the balanced chemical equation right here, and we did an experiment where we measured the concentration of NO2 over time. And then, so here's this data that we collected, concentration versus time. And then we made 3 graphs using that information. So this first graph here is we just plotted concentration versus time. And notice how this is definitely not linear. It's really steep at first, then it slows down. So then we also plotted the natural log of the concentration versus time. So we just went in and using our calculator, we found the ln button on our calculator and took the natural log of each of these values and plotted that. And then we took the inverse of each of these values, so like 1 over this, 1 over this, 1 over this, and plotted this right here. And what we should notice is when we look at these 3 graphs, only one of these graphs is going to be linear. And it looks like this graph right here is the linear one. So now let's look back and see, remind ourselves what that means there. Okay, so if the inverse of concentration versus time is linear, that means it is a second order reaction. Okay, so you said this equation has the inverse. So if this relationship is linear, then it's second order. All right, so it looks as if this is a second order with respect to, it's second order with respect to NO2. And NO2 is the only reactant, so we can write our rate law already. So rate equals K NO2 squared. And notice in this case that you may or may not notice that the 2 happens to match the coefficient here. But remember, that is not how we determine the exponent. So sometimes the exponent may match the coefficient, but other times it may not. And we can't figure out the rate law just from looking at the balanced chemical equation. We have to look at some sort of experimental data to figure this out. All right, and then we want to find the value of the rate constant. So this is the answer number 1. What's the rate law? Number 2 says find the value of the rate constant. And we may have done problems before where we've done this. We've just rearranged and said K equals rate over NO2 squared. And that's a great way to solve for K if we know the rate. But if you look at our data, we don't have any rate data. We just have concentration versus time. So we could find like an average rate, but that wouldn't be what we need here to solve. So now remember, whenever you have concentration versus time data, there's another equation we can use, right? So let's go back and look over here. We just realized that this reaction was second order, so that means that we can apply this equation right here, and we can plug some numbers in to solve for K. So I'm going to use this equation right here, and I'm going to start plugging in some numbers. So the way this equation works is it's 1 over concentration at time t, that's how we interpret that, minus 1 over the concentration at time 0, equals K times T, which is time. So I'm just going to pick, so let me start filling these in. Well, the concentration at time 0 is 0.07 molar. And then I'm going to pick some time point. It doesn't matter which time point I pick. Actually, let's pick this one right here. All right, let's pick 100 seconds. So K is our unknown, so I'm going to still leave that as K. But then my time is 100 seconds. And then this right here, this first value is going to be the concentration at 100 seconds. So this number is going to be 0.015 molar. All right, so I'm going to plug that in my calculator. 1 divided by 0.015 minus 1 divided by 0.07. And then I'm going to divide by 100 seconds in order to solve for K. So I take this minus this divided by 100, and I should end up with 0.52. Now let's figure out what the units are of this number here, because units are always really important. Notice the number on the top, the value on the top is 1 over molarity, and then it's divided by seconds. So let me rewrite that. I'll write that over here. So 1 over molarity divided by seconds, you can think of that as 1 over molarity seconds. Let's just consolidate that and put them both on the bottom. Or we can write it this way, m minus 1, s minus 1. So that's the units of your rate constant for this reaction. And remember, the units of your rate constant are going to vary based on whether it's first order, second order, etc. So just make sure you pay attention to the numbers you're plugging in here when you're solving for k to help you figure out what the units are. So the units are just important as the value itself. Like if this were a test question on the AP test, maybe it'd be a 2-point question and you get 1 point for the value and 1 point for the units. Or maybe it'd be a 1-point question and it's all or nothing. So if you got the value right, but you got the units wrong, you would get 0 points. So units are really important there. Here is another problem here. And this one, we're not looking at graphs here, but we're just kind of reading through this problem. And if we read through this, let's look at the information we know. We've got a rate constant given. So we've got a k value given here. It's 1.45 years, -1. And we've got a concentration, some initial concentration. So I'm going to label that A sub 0. That's the concentration times 0. And that's 5 times 10 to the -7 grams per centimeter cubed. So that's a different unit of concentration here, and that's okay. And the question is, what is the final concentration after some amount of time has passed? And now let's read through the question to interpret how much time has passed here. So we're talking about some insecticide being washed into a lake on June 1st of 1 year, and then we're asked what it's going to look like on June 1st of the following year. So what that tells me is that 1 year has passed. So my t equals 1 year. And this problem also tells me that it is a first order reaction. So that's important to know, because remember with the integrated rate laws, there's some different equations, and yeah, you have to know which equation to apply here. So let's go over and look at our integrated rate law for first order. That's going to be this one right here. Okay, your first order integrated rate law. So I'm going to go and apply this one. And again, remember, these are on your equation sheet, so you don't need to memorize what those integrated rate laws are. So here is my integrated rate law here. It's the, so it's the natural log of the concentration at time t minus the natural log of the concentration at time 0 equals -k times t. So we're going to start plugging the values here. The concentration of A at time t, that's our unknown. The concentration of A at time 0 is 5 times 10 to the -7 grams centimeter cubed. The value of k is 1.45 years to the -1, and then time is 1 year. So notice how our years will cancel over here. So this value over here on the right is going to be unitless. And that's what happens actually when you take the natural log of something, or just the regular log base 10 of something, is that the answer to any log value is actually going to be unitless. So that's something we'll see later on with pH as well. All right, I'm going to pause here and give myself some more space. Okay, so now we've got a little bit more room here. So this first value is, again, our unknown, the natural log of A at time t. That's what I'm trying to solve for. And then minus the natural log of 5 times 10 to the -7. If you plug that in your calculator, you get that's -14.5. In these type of problems, it's going to be really important to be careful with our negatives and positives and just double check all those here. And then remember over here on the right, this is -1.45 times 1. So over here, this is -1.45. These values are both unitless. Over here, that's because the years canceled out. And over here on the left, it's because it's a log value. So I'm just going to write that over here to the side. If you take the natural log of something or the log of something, you will get a unitless value. So log values are unitless. Okay, so now I'm going to rearrange this. So the natural log of A sub t is going to be negative 15.95 when I rearrange this, because then you're going to be adding a negative. And so again, just be really careful with sign. That's a way you can easily make mistakes on this type of problem, is getting all our negatives mixed up there. So how I'm going to solve for this is what's the opposite of a natural log is doing e to the. So if you look on your calculator, it's going to look different on different calculators, but you might see a button, your calculator button, that says ln, looks like this, and then right above it, it might look like this, e to the x. Again, each calculator is different, but these are kind of the opposite functions of each other. So the opposite of natural log is raising something e to that value. Okay, so what that means is to solve for the concentration at time t, I'm going to raise e to the power of negative 15.95. So you can stop and plug that in your calculator, and you can, if you're not sure how to do that, you can ask someone else who has a similar calculator, or you can show me what your calculator looks like. You can take a picture of it and send me a picture, so I can help you figure that out. Now when you plug that in your calculator, you're going to get 1.17 times 10 to the negative 7. And you might wonder, what are the units here? Because this is a unitless number. So the way you figure out the units of concentration, it's just going to be the same units as whatever this concentration is. So here we are measuring the concentration in grams per centimeter cubed. We're used to measuring a molarity, but this one's a little bit different. It's grams per centimeter cubed. But that tells us my answer is also going to be in grams per centimeter cubed. All right, let's try one more problem here with this kind of calculation. So this is the same problem. It's part B, and we're looking at how long will it take for the concentration to decrease to a certain amount here. So remember, all of the things that we knew from the previous slide still hold true. So we know it's a first order reaction. So this equation is the natural log of the concentration at time t times the natural log of the concentration at time 0 equals negative kt. And we want to know how long it will take to decrease to 3 times 10 to the negative 7. So that's what our ending concentration is going to be, 3 times 10 to the negative 7 grams per centimeter cubed. Initial concentration was this, 5 times 10 to the negative 7 grams per centimeter cubed. And then our value of K was given. Remember, the rate constant is 1.45 years to the negative 1. And then time is our unknown in this case. And again, remember, with this type of problem, especially with these natural log problems, just be really careful with sign. So the natural log of 3 times 10 to the negative 7, if you plug that in your calculator, that's negative 15.02 minus negative 14.51. So be careful because you're subtracting a negative. And these two are unitless, because remember I said log values are unitless. And then over here, this is negative 1.45 years to the negative 1 times time. So if I'm going to rearrange this and solve for time, I'm going to divide both sides by this value right here, negative 1.45 years to the negative 1. So this cancels out, and I'm left with time is equal to 0.35 years. And again, if you thought you're like, oh, I think I did the same thing, but I got a slightly different answer, just go back and double check your signs and see if you somehow like dropped a negative somewhere, because that's the most common source of error here, because it can be hard to keep track of all these negatives. And if you're thinking about the units, the number on the top was unitless, and then the number on the bottom was the inverse of a year. So the inverse of an inverse is just, you get back to the original. So your answer here is in years. All right, so let me know if you have any follow-up questions.